Okay, let's get right into this. A new paper just dropped from the AI lab Deepseek. And trust me, it's a big one. They're taking aim at a foundational concept that has been quietly powering pretty much every major AI model for the last decade. And if they're right, well, this could completely change how we build the most powerful AI models, period.
Just let that sink in for a second. In a field that moves at the speed of light, the core DNA of models like GPT-4 and Llama 3 is literally built on a principle from way back in the early 2010s. It worked, it scaled, and pretty much everyone just assumed that was the only way to do things. But Deepseek is basically stepping up and saying, hold on.
So to really get what Deepseek pulled off here, we have to go back. We need to understand this 10-year-old idea, and more importantly, the hidden trade-off that everyone just sort of accepted as a fact of life. Let's dig into the bottleneck.
All right, so the idea is called a residual connection. Think of an AI model like a giant skyscraper with hundreds and hundreds of floors or layers. Now, during training, a signal has to travel all the way from the top floor to the bottom to tell the model how to get better. The problem was the signal would get lost or just, totally garbled on the way down. Residual connections? They basically built an express elevator, a shortcut that let the signal zip past all the floors and arrive safe and sound.
And wow, what a difference it made. Before this, trying to build really deep networks was a total nightmare. The deeper you made them, the dumber they got. Residual connections changed all of that, like overnight. They literally saved deep learning from hitting a brick wall. Training became stable, reliable, and it just worked. It was so successful that it stopped being an idea and just became part of the furniture. It was how you build AI.
But here is the catch. See, that express elevator, that residual connection, it worked because it was so narrow. But that was also the problem. All the incredibly complex information swirling around inside the model had to get squeezed through this one tiny little channel. For years, that was fine. But as models got bigger and the problems they were solving got way harder, this little bottleneck that no one really talked about started to become a real drag.
So naturally, people tried to fix this, right? The obvious move was to just make that narrow path wider. But this seemingly simple upgrade led to this totally catastrophic, unpredictable failure.
This new idea, it was called hyperconnections. The thinking was, instead of one express elevator, why not build a dozen? Give the model a bunch of parallel streams to move information around. On paper, this is a total no-brainer. You're giving the model way more room to think, more workspace for complex reasoning. It should have been a huge upgrade.
Yeah, it wasn't. What would happen is, at first, everything would seem great. The model's learning, performance is going up, but then, deep into a very expensive training run, total disaster. The different streams, these different elevators, they'd start talking to each other, and not in a good way. They'd create this crazy feedback loop. Signals would amplify and just explode, and the whole training run would just poof, collapse, suddenly, no warning. And that instability made hyperconnections just way too risky.
This is the exact problem Deepseek went after. And they didn't just try to patch up the instability. They found a way to stop it from ever happening in the first place, with a solution that is just so elegant. They call it, and it's a mouthful, Manifold Constrained Hyperconnections. Let's just call it MHC. Now, the name sounds super complicated, I know, but the actual idea behind it is incredibly smart and pretty simple. Instead of just letting those information streams run wild, they put them on a mathematical leash. And you can really see the difference here. The old way, unconstrained hyperconnections, that was just chaos. MHC, it's all about control. Deepseek's method lets information get shared between all those streams, but there's one golden rule. The total amount of signal, the total energy in the system, has to stay the same. It can move around, but it can't just grow out of control.
And this is the brilliant part. It's not just some lucky trick. It's a mathematical guarantee. By basically forcing the way these streams mix to stay within a specific mathematical shape, it's called the Birkhoff polytope, they make sure it can't explode. Stability is baked right into the design. They figured out how to get the best of both worlds, the huge capacity of having many pathways, but with the rock-solid stability of having just one.
Okay, so the theory is beautiful, right? But does it actually work in practice? This is where the results and Deepseek's incredible engineering really shine. And the payoff is just, wow, it's immediate and it's clear. Take GSM-8K, which is a super tough math benchmark. A standard model gets a score of 46.7. The exact same model, but with MHC swapped in, jumps to 53.8. That is a huge jump in reasoning just from this one architectural change. That's insane.
And nope, this wasn't a one-off thing. Across all these different tests for logic, knowledge, you name it, the MHC models just consistently crushed the old versions. I mean, these are the kinds of improvements that entire research teams would kill for, and they'd spend years trying to get them.
So what's the big picture here? It adds up to this: a 400% an increase in the model's internal communication capacity. They basically gave it a 4-lane superhighway where it used to have a tiny back road.
Now, normally you hear a 400% boost and you think, okay, what's the catch? The training must take forever now, right? But check this out. The total increase in training time was less than 7%. That's just mind-blowing efficiency. So how on earth did they do that? Well, this is where the pure, hardcore engineering comes in. They got their hands dirty. They wrote custom code for the GPUs, used some really clever tricks to save memory, and basically engineered their way around one of the biggest roadblocks in AI today, this thing called the memory wall. So you see, it wasn't just a brilliant idea. They actually did the incredibly difficult engineering to make that idea usable in the real world.
Okay, so let's zoom out for a second, because this paper, it's more than just a technical report. It's a strategic move, a signal flare on the global AI chessboard, and it says a lot about Deepseek's confidence.
Just like analyst Wei Sun points out, this is Deepseek basically planting a flag and showing the world, hey, we're not just following the leader here, we're innovating. They're solving fundamental problems, finding their own way around big constraints like chip access.
And the fact that they published this for everyone to see, that's also a really big deal. As Lian Zhensu from Omiya puts it, this shows real confidence. The strategy seems to be, let's share our foundational breakthroughs, push the whole field forward, and we're confident we can still build the best stuff on top of it.
Which, of course, brings us to the million-dollar question. What is next for Deepseek? I mean, you remember their R1 model, right? That was a huge Sputnik moment for a lot of people. But then, the sequel, R2, got delayed. Apparently, the founder just wasn't happy with it. So now everyone is wondering, could this be the missing piece? Could this MHC tech be the secret sauce that finally powers their next big model?
And that really brings us to the final and maybe the most mind-bending question of all. For 10 years, a decade, the entire AI industry just assumed this one way of building models was the only way. Deepseek just proved that's not true. So it really makes you think, if a 10-year-old idea that we all thought was solved wasn't actually optimal, what else are we taking for granted? What other fundamental truths about AI are just waiting to be completely overturned?